So I've scrolled back up now to the binary character encoding. When I was going through the first lesson, I mentioned to you that we have machine language is the only language that the computers, the CPUs, actually understand. So the question you might be wondering is, well, how do we then represent things like alphabetic characters or numbers, or then even more complex sound and video? How do we represent all that information then in a world where everything can only be zeros and ones? Well, the answer to that is we have a process that is known as encoding. I have it bolded right here, encoding. And so there are, depending on the particular technology that we're looking at, or the particular type of data that we're looking at, there's these different ways then of representing the data as patterns of zeros and ones. And so that, again, is called the process of encoding. So when we, say, have a person using our program, and we request input from that user within our program, and the input we're looking for is to have them type in some characters from the keyboard. As each key on the keyboard is being pressed, that key that was pressed creates an encoded value that represents to the CPU the actual character then that was being pressed from the keyboard. And so the way that the computer understands that particular encoding is that there's what we call a hash table, which is basically a table that says if you see this sequence of zeros and ones, then and this is more for the humans to be able to understand things. The table shows, well, if it's this pattern of zeros and ones, then here's the actual character that's being represented. So I'm going to click on the link here that reads ASCII character coding. And ASCII is the American Standard Code for Information Interchange. So it's an acronym, ASCII, and it's pronounced ASCII. And the original ASCII was developed on computers that were only 7-bit systems. So 2 to the 7th power is 128. So what that tells us is that we can only represent then 128 characters using the original ASCII because it was only a 7-bit system. They later came out and they extended ASCII. Once we got 8-bit computers, actually we had 8 bits, but they were only using 7 of those bits at the time. The last bit was a parity bit. But anyway, they advanced that and they used all 8 bits. So now 2 to the 8th power is 256. So now we could represent 256 characters. Problem is, I mean, if you think about like the English alphabet, we only have 26 characters in it. And then we've got some numbers 0 through 9 that represent the decimal system. And we got a few symbols like percent signs, dollar signs, but nowhere near 256 characters. However, when you get to Asian languages, they have thousands of characters in their languages, in their alphabets. So the ASCII and the extended ASCII character sets would not support those languages. And so now we've evolved to a 16-bit character set, which is referred to as Unicode. So let me show you how this works. I'll just scroll down to the first table that we have here. So this is the first 32 characters. See, we start at 0 and end at 31, so that's 32 characters. So you can see these are not printable characters. These are things like the bell on the computer and the line feed and carriage return and things of that nature. So when you press the enter key there on your keyboard, you're actually sending in this character code, which is this machine code right there. So that's what a return character, or that's what the enter key looks like to the CPU when you press it. 4 zeros followed by 1, 1, 0, 1. So that then would, based on that pattern, then that instructs the computer program to basically move the cursor down below the current line that it's on. So for humans, we know it as the carriage return. We might even recognize it by its numeric value, its decimal value, but this is, again, is what the CPU is always going to see that as. Now, as we go down further, you see we start getting into some actual characters. So there's your quote and your exclamation point, the hashtag or number symbol, $, percent, etc. And you can see, again, they're all numerically represented here. So now we're looking at from 32 to 127. And again, have the binary values to the left. That's what the computer needs. The CPU needs to be able to actually understand which one of these characters it is that has been typed in from the keyboard. And we get further down, now we get to the extended ASCII character set. So you can see all of our alphabet, the English alphabet's covered here. So characters have case, notice it is case sensitive. So a capital letter A is 65, whereas a lowercase a is 97. So there is that, designation, that difference identified, whether it's capped or lowercase. So we do get the whole alphabet there within the first 128 characters, but then we get some other symbols available once they extended it with the extended ASCII character set called ANSI, A-N-S-I. And so you can see this is just, bullets, some fancy quotes, trademark, copyright, registered trademark, all kinds of symbols that we may need, but not quite as common in most of our printing or output or even input. And then finally, here's a link to the Unicode tables down here. This takes us to the wiki page that has some good information on Unicode for you. And really, you don't need to go in any great depth on this. Just know that we now have a 16-bit character system, and it is backwards compatible with ASCII and ANSI. So the first 128, or I should say first 256 characters in Unicode, exactly the same as they were in ASCII and in ANSI. So it's only once we get above the 256 here that we start seeing other characters that are now available to us that weren't previously available until we started using Unicode. So that's called encoding, taking what would really be kind of I'm trying to think of a good word for it, an analog, I think would be the best way to say that, an analog information, meaning humans pressing keys on the keyboard and then converting that to digital information, meaning the zeros and ones then that represent the keys that are being pressed. And so that's what actually gets stored in the memory. And that's also, again, when your program is being run and it's compiled into zeros and ones, once the user double clicks on your executable file, it's taking all of those zeros and ones and actually loading them up into RAM. So it pulls it in from storage at that point, loads them up into RAM, and then the CPU starts grabbing the lines of code as necessary to load into what they call a stack. We'll get to the stack a little bit later on, but that is a data structure, and that's the data structure that the CPU uses to list each of the commands and then start processing one by one. So, with that said, I want to introduce you to the fact that it would be a good idea for you to get a pretty good understanding of how to convert decimal values into their binary equivalent. So right above the ASCII character encoding box that I have there, you'll see I have another box that reads the binary numbering system. When I go ahead and click on that link, I get to this video right here, which is a good video to watch. This is going to show you and explain to you that encoding process.
Hi, my name is Lamore Freed, and I'm an engineer here at Adafruit Industries. And this is where I do engineering and design, and I design circuits for fashion and music and technology.
My name is Federico Gomez Suarez, and I'm a software developer with Microsoft Hack for Good. And I look into using technology to help us solve some of the big social problems of our times.
You may have heard that computers work on ones and zeros. Or you may have seen scary looking visuals like this. But almost nobody today actually deals directly with these ones and zeros. But ones and zeros do play a big role in how computers work on the inside.
Inside a computer are electric wires and circuits that carry all the information in a computer. How do you store or represent information using electricity?
Well, if you have a single wire with electricity flowing through it, the signal can either be on or off. That's not a lot of choices, but it's a really important start. With one wire, we can represent a yes or a no, true or false, a 1 or a 0, or anything else with only two options. This on-off state of a single wire is called a bit, and it's the smallest piece of information a computer can store. If you use more wires, you get more bits. More ones and zeros, with more bits, you can represent more complex information. But to understand that, we need to learn about something called the binary number system.
In the decimal number system, we have 10 digits from 0 to 9, and that's how we've all learned to count. In the binary number system, we only have 2 digits, 0 and 1. With these 2 digits, we can count up to any number. Here's how this works. In the decimal number system we're all used to, each position in a number has a different value. There's the 1 position, the 10 position, the 100 position, and so on. For example, a 9 in the 100 position is a 900. In binary, each position also carries a value, but instead of multiplying by 10 each time, we multiply by 2. So there's the 1's position, the 2's position, the 4's position, the 8's position, and so on. For example, the number 9 in binary is 1001. To calculate the value, we add 1 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1. Almost nobody does this math because computers do it for us. What's important is that any number can be represented with only ones and zeros, or by a bunch of wires that are on or off. The more wires you use, the larger the numbers you can store.
With 8 wires, you can store numbers between 0 and 255. That's 8 ones. With just 32 wires, you can store all the way from 0 to over 4 billion. Using the binary number system, you can represent any number you like. But what about other types of information, like text, images, or sound? It turns out that all these things can also be represented with numbers. Think of all the letters in the alphabet. You could assign a number to each letter. A could be 1, B could be 2, and so on. You can then represent any word or paragraph as a sequence of numbers. And as we saw, these numbers can be stored as on or off electrical signals. Every word you see on every web page or your phone is represented using a system like this. Now, let's consider photos, videos, and all the graphics you see on a screen. All of these images are made out of teeny dots called pixels, and each pixel has a color. Each of the colors can be represented with numbers. When you consider that a typical image has millions of these pixels, and a typical video shows 30 images per second, now we're talking about a lot of data here.
Every sound is basically a series of vibrations in the air. Vibrations can be represented graphically as a waveform. Any point on this waveform can be represented by a number. And this way, any sound can be broken down into a series of numbers. If you want higher quality sound, you would pick 32-bit audio over 8-bit audio. More bits means a higher range of numbers.
When you use a computer to write code or make your own app, you're not dealing directly with these ones and zeros, but you will be dealing with images or sound or video. So if you want to understand how computers work on the inside, it all comes down to these simple ones and zeros and the electrical signals in the circuits behind them. They are the backbone of how all computers input, store, process, and output information.
So essentially, if it's quantifiable, then we can convert it to some sort of a digital format. And they also emphasize there, which I want you to make a note of to yourself, that the more bits we have available to us, the more complex information we can encode. So now that you understand the basics of how binary numbering system is used within the computer, we can go ahead and move you over to our next tab here, which is our binary practice screen. So the idea here is that we just pick a number between 0 and 255. We should be able to, using these tiles here, turn on the ones and the zeros to make that decimal value and show the representation, what it's going to look like in binary. So for instance, if I wanted to do the number 129, and I'm not sure, yeah, I guess they did make it clear in the video. So the way that the binary works is where we have zeros, we don't use the value from that column. If there's a bit that's turned on, meaning it's a 1 value, then you do use that value from the column. So just a simple example, if I want to represent the number 129, I would turn on the bit that represents the value 128, and then I would turn on the bit that represents the value 1, and you can see that then is the binary representation of the value 129.
230?
230. All right, so 230, we'd have to at least turn on the 128 bit. And in fact, here's a good way to break this down. Always start from the left, work to the right. And so our target number now is 230. And so the idea is when I'm starting from the left, the first question I want to ask myself is, can I subtract that number 128 from 230? And I can. So since I can take that value, subtract it from the target number, I'm going to turn that bit on because I know it's going to require at least that amount to get to our goal as far as the number we're trying to create here. So then I'll go to the next column. Well, actually, we'll have to do the math here now. So let's take $128, subtract that from 130, and we get a remainder of 102. So I just wrote that down on a piece of paper, did the math real quick. I guess I could have called up my calculator, but I was too lazy for that. So that means now I'm looking at a target number of 102, essentially, while we continue to turn on these bits. And each time we turn on a bit, we do that subtraction process to see, what our remainder is after we've turned on the previous bit. So now I'm going to ask myself, can I subtract this next bit value, 64, from our current value, 102? I can, so I'll turn that bit on. So now let's subtract 64 from our previous remainder. That should give us a value then of 38, if I did my math right. So then my next question is, can I subtract 32 from 38? I can, so I'll go ahead and turn that bit on. Then I'll go ahead and subtract the 32 from my 38. That's going to leave me a value of 6. So I'll ask myself, can I subtract 16 from 6? I cannot. So I'm going to go ahead and skip that one, right? Can I subtract 8 from 6? I cannot. Yes. So I'll leave that 0. Can I subtract?
You can't? Wait, you can't?
8 from 6? I'd get a negative value, right? If 6 is my current value and I subtract 8, I get -2.
Okay.
Right?
You was confusing me earlier when you were doing the math, so.
Sorry. So I can't subtract 8 from 6, but I can subtract 4 from 6. So I'll turn that on. Subtract 4 from 6, we're left with 2. And so that means if I subtract, I ask the same question, can I subtract 2 from 2? I can. So I'll turn that on. And now we're at our value, so we know that we don't turn on the 1 bit there because we're at 0. So I took the original number, that 230, and I just went from left to right, and it's a simple math problem. What's the first bit that I can subtract from our target number? and we knew it was 128. Then subtract the 128 from your target number, leaves you 102. Can you subtract 64 from 102? You can. Turn that bit on. So now we got to subtract 64 from the 102. That left us with the 38. Can we subtract 32 from 38? We can. So we turn that bit on. Now we're left with the remainder of 6. And so we weren't able to turn on the value for 16 or 8, but we could subtract 4 from 6. That left us with the remainder of 2. So then we subtracted or added, turned on the bit for 2, and that gave us then the actual number we're targeting, right? 230. So that screen is strictly for practice to take the concept that I just introduced to you. So, later on after class, I highly recommend you come back here. Just start writing down numbers on a piece of paper. It'll always be between 0 and 255. Just pick a number at random and then see, starting from the left to the right, see if you can work out the problem so that you can get the binary representation then of the value that you want to target. Once you have done that, we can take it a step further back to the page that we're on where you watch the binary video. It was the conversion practice I was just showing you. But now I have created this competitive version of what you just saw. I called it Converter. The idea here is I put in my first name and my last name because we want to have your scores recorded to the scoreboard. And this is going to give you a 1-minute time frame and randomly generate decimal values for you. The goal is to see how many conversions you can do within a minute. So I'll demonstrate it to you. I'll click on New Game. I've been given the number 5, so I know that's a 4 and a 1, and it tells me that's correct. So now I choose New Number. Now here's my next number, 121. So I know that I can't use 221, so I can use 128. And if I add 64, I get 192. We're still short by 29, so I can't use 32. I could use 16, 8, and then 5. So now I got that correct number. Click New Number again. So I'm just going for the whole minute now. 49 is 32 plus 16, which is 48, plus 1 is 49. New number. 162, new number. 144, new number. 99, and I'm running out of time now. Yeah, so I got 6 conversions there. That's my score, is 6 conversions. So if I want to, I can add it now to the scoreboard by clicking on this button, Add to Scoreboard. And then if you want to view the scoreboard, you click on this button here, Scoreboard, or you could start a new game. If you didn't think you did well enough at that first attempt, keep doing it. The more you do it, the better you get at it. But if we click on the scoreboard now, you'll see that everything is sorted by the highest scores here. And I only got a 6, so I'm way down here at the bottom. Let's see, right there, this is the one that I just posted. So you can see that over the past few years here that I've been running this game, we've had quite a few students participate, and the current high score is 17. So that's your goal, to see if you can do as well or better. And if you don't worry about it. As long as you make an attempt on this converter game and you actually post your results to the scoreboard, whatever the score is that you get, I will add that as extra credit in the grade book for you. So if you get a 6, you get 6 extra points. If you got a 17, you get 17 extra points in extra credit. Does that make sense? Anybody need me to give you more detail on that?
The only question I have is, are we allowed to do it more than a couple times?
Oh, absolutely. Try it 100 times. I would highly encourage you to do it that many.
Great, cool, thanks.
So the whole idea of this is just to really, etch into your gray matter there, this concept of the binary and the fact that everything has to be converted to binary, and we can actually represent just about anything. Like I said, anything that's quantifiable, we can represent it as a binary value in the computer.